So you've started a babysitting part-time job to pay for your textbooks and your other courses, not this one, right? There's no textbook. So you put your name out there on Facebook, on flyers, however, you've got your name out there, and in a matter of like days, you're getting phone calls. So the first person that calls you will call Mom A. And she calls you, and she needs you for 3 hours. She's going to pay your rate. That's a pretty good price for a babysitter. So for 3 hours, if not, I'm getting ripped off. And she has 5 kids.
Cool.
And because she has 5 kids, she's a busy lady, and she says that the average age of her kids is 5 years old. So she kind of talks about them as a unit, right? The average age is 5 years old. So you're kind of excited, you've got some business pretty quickly, but in the midst of this conversation with Mom A, the call waiting goes off, and you get another phone call. We're going to call this caller Mom B. And she wants you, and she needs you for for 3 hours. She's going to pay you your rate. She has 5 kids. What state are we in? You don't get my joke from last class?
Yeah.
Utah, right? These large families. 5 years of age as well. So what are the odds that these two moms have kids exactly the same age? In other words, they would be like little
Rugrats.
They are probably rugrats, but they would be kids that are exactly the same age. Pretty small likelihood that they're exactly the same age. So the parents, the mom's telling you the mean isn't really enough to understand what you're getting into, right, as a babysitter. You have an idea, it's better than nothing, but these could be really different families, and depending on your babysitting style, you might just want one family over the other. So you need more information. The mean itself isn't enough, and this is the whole point. We need another measure. So you click back over to Mom A, and you say, well, what are the ages of your kids? And she says, okay. She doesn't mind giving it up. So she says 1, 2, 4, 8, and 10. Okay, thanks. Hold on. Click back over. Mom B, what are the ages of your kids? I don't know if this is physically possible, but this is how it works in my example. I don't know if you can have kids exactly the...
Yeah.
You can? Okay. So the average of both of these, if you take a minute, is 5, in fact. But they're really different families, right? And according, again, with your babysitting style, they're really different, maybe, depending on how you like to manage 5 kids when you babysit. So we need something more beyond this. So the standard deviation is going to offer us another way to describe the data that'll give us more insight into how similar or not similar the ages are of the kids. So your intuition is, which ones, if you don't even know what really standard deviation is beyond that sentence, which one of these families will have a larger standard deviation? What do you think?
Mom A.
Mom A, yeah. So we're gonna find that this one has a larger standard deviation because the ages are more spread out. And this one's going to have a smaller. Those are our hunches. So let's compute a standard deviation. We'll do a little table here. And we're only going to compute one. This will be the only standard deviation I will ever compute in front of you in class with pen and pencil or marker and board. The rest of the time we're going to let software do it. But it's good to walk through one of these so you get a better understanding of what this thing standard deviation really does. So, and again, this is a really tiny data set. We'll do Mom A. There's only 5 values in the data set, so it's really easy to do it. So we're going to have a table. So I tried to give you most of the page there to do this. And we're going to do Mom A's kids. So we'll say, let X be the ages of the kids. we have the 1-year-old, the 2-year-old, the 4-year-old, the 8-year-old. We have plenty of room here, so I'm just spreading it out.
I have a question.
Yes.
How do you know what to put where? So how did you know to put the age of the kids under X?
I just wanted to list the data out, and I like to list my data vertically when I do math on it, as you saw earlier with the other table. I could have called this W. I could call it anything I want. So I guess we overuse that letter X in any math class. It seems to be the one we go for first. I could call it Y, C, anything like that. So 1, 2, 4, 8, and 10. So it said, the definition stated it's the average deviation. So what I want to do first is figure out what the deviations are. In other words, how far away are each of these ages from that mean age of 5? So this is sort of symbolic, but what I'm going to do is take the 1 and subtract off the mean, and take the 2 and subtract off the mean. So it's very, notice I'm not even doing the math yet. I'm doing the repetitive process of repeating this mathematical operation over and over. This is why machines are brilliant at finishing this for us, because they can do things like this really fast. If I don't do this, it'll be all warped.
Does that formula have a name?
Right here?
Yeah.
It will eventually. Right now, y'all can see the way I teach. I'll run you through it without the formula because I want you to see the sort of the intuitive approach to it, and I'll show you the formula in a minute. Actually, you could probably write the formula for me once we finish it, I think. Or at least nod your head and go, I know exactly where that formula came from. So if we want to find these deviations. So this is 4 years, right? Under -4. This is what?
-3.
Yeah.
-1.
-1 or 1 year's below average.
3.
3 above, and 5. So we call it the average deviation. I got deviations here, right? Do you see them? These are deviations, or distances, if you don't like the word that. Those are deviations. If we add them up, what do we get? Because we're going to find an average, right? You add them up and do some dividing and such. If we add them up, we get 0. And this happens in most of all cases. You add them up, and the ones that are below the average will cancel out with the ones that are above the average. Probably because the average is that sort of central balance point. Think about it. So we can't take just pure deviations, although that's what we want to get at. So how do we force numbers positive? Because the negative and positive aspect of this is what's causing it to sum up to 0, unfortunately. So what's a mathematical thing we can do to numbers that forces it positive? There's a couple different things you might have learned in an algebra class that you can do to a number, and the output will always be positive. Any ideas?
Square it.
Square it. Yeah, that's what they came up with. Now you can absolute value numbers as well, and that's one of the things they kind of chewed on as to what to use for this process when they were coming up with it. But the squaring one out is the most popular way of doing this. So our next column will be x minus x bar quantity squared. So I'm just going to square the deviations. So if you want to think about this, this is deviations. Squared.
And why are we squaring it?
To force some positive. Because this negative positive feature here, some being below average and some above average, are causing them to add up to 0, and we can't really do much with 0. We know there are some deviations here, right? They clearly aren't all 5. So we have to sort of do something mathematical to it in order to force them positive. So in this case, the deviation here is -4. What am I going to do to it? square it. The deviation in this row was 3 years under the average. So I'm just taking these numbers that I found as the measured deviations and I'm squaring them all.
So you would square using the positive ones?
Mm-hmm. I have to treat them all the same so that in the end I can do some sort of meaningful interpretation. So again, I did all the sort of work and now I'm going to go through and do the actual computation. This makes for a positive 16,
9,
9,
1,
1,
9,
and
25.
all right. Now these are clearly not going to go to 0. They're all positive. So if I add these together, what do I get? I get 10, 35, yeah, 60. I get ready for it. 60 years squared, right? Because I squared my value. So instead of having just regular years, I have years squared. We'll deal with that in a minute, but we have to keep in mind that this isn't just 60 years, it's 60 years squared. And the only unit I really understand squared is feet. Or, right? Because we can see tiles on the floor, and we've kind of grown up to understand what square footage is. I don't know what squared years are. And I'll have to fix that in a minute, but for now I'm going to deal with it. So these are our deviations squared. Now, we added them up. Now, what do we typically do after we're trying to find sort of the average deviation? We would then divide
by the number of kids.
by the number of kids. Now, in this case, we're going to divide by 1 less. 4. We don't divide by the pure sample size. We divide by 1 less that's in the sample. And they found with all their research and stuff they did over the years, hundreds of years ago, that this gives a better measure of that average deviation. Not to divide by your sample size, but to divide by 1 less thing that is in your sample. So what does that give us? 15 years squared. Still having a hard time understanding what that means. So one of my fixes to get out of the negative positive was to square my data values to get out of that jam. What's the mathematical opposite of that I could do to reverse that process right now? Yeah, you have a question.
Was it 1 less the number of kids or 1 less the...
That's a good question. It so happens that both of these are 5. It's 1 less the number of kids. So in both of these, n equals 5. So this is my sample size, 5 kids. So I need to reverse that squaring so I can get it back to something interpretable. And I wish this were a 16 because that's really easy arithmetic, but it's not, so I might need someone's help with a calculator. I do know that years squared will go down to years to the first power when I square root it. And this is 3 point something, I forget.
3.87.
3.87. 3.87 years. This is our standard deviation. This tells us how these ages deviate from 5, how on average they deviate on 5, deviate from 5. You know, some are, as you can see the deviation, some are a little bigger, some are a little smaller, but on average they deviate by about almost 4 years, a little under 4 years.
And that's just mom A.
That's mom A. Now, you have a little S equals at the top of your notes. This is the formula you just did. Let's see if we can come up with it. You can fill it in up there. Hopefully you still left a little space in there that S equals, anticipating something at some point. S equals, well, what do we do first? Let's just walk through our process. What's the first thing we did? We took our data values and subtracted off the mean. All right? Just move over a little bit, leave a little space. All right? So we calculated the deviations. What's the second thing we did?
Squared.
We said, oh man, we got to square these. Excellent. We squared them. And then remember what happens when we add up things? What's an easy way to say that in math now? We added up everything in this column. So we have a sum, right? That's my little sigma. Let me make it more pronounced. We added them up, right? And then we divided by n minus 1. Right? One less than it was in our sample. That's the 4 underneath. So we added them up. We divided by 4, one less than a sample. And then to fix our fix, right, our quick fix of squaring, we had to square root. This is the formula you will see in every statistics book or every intro stat book for standard deviation. And I showed you that first, y'all would have not listened to me. I just learned over the years. The minute I put that formula first, people were like, oh God, here we go. But again, hopefully, much like what we did with the mean of the frequency table, this kind of makes sort of common sense, that this is how they would try to quantify and figure out how much they deviate from the middle of the data. 3.8. So S here for Mom A, her S is 3.87. And notice the unit is in the same unit as the mean, so they're a really nice little pair to talk about together. That's why I took the square root and didn't just leave it like this, because I wanted back to the same unit we started with, which was years to the first power, how we all kind of talk about time. I'm not going to do Mom B this way. I'm going to do Mom B on the computer, and I'll show you how to use StatCrunch.
Let's see how StatCrunch can help us find standard deviations. The first thing you're going to want to do is to log into StatCrunch, and once you do, you will see this screen. Let's hit Open StatCrunch since we're going to key our data in manually. Take my first column called var1, and I'm going to use it to represent Mom A and her children's age. So that was 1, 2, 4, 8, and 10. I'll take column 2 here and put Mom B in. Her children's ages were 3, 4, 5, 6, 7. So you'll have to take a moment in some cases in this course and type your data in. In other cases, I'll have the data stored somewhere and I'll instruct you where to find it. To compute standard deviations, we're going to visit the same place we did to find means and medians. We'll hit Stat, Summary Stat, Columns. Let's choose Mom A. Select the columns you'd like. It'll advance it over here. The default setting here, all these highlighted in blue are repeated over here, so they're already chosen for you. And we can hit Compute, and again, those are the default measures. And we get this right here. Now let's take a look. You can see there's 5 in the data set. The mean, in fact, was 5 years of age. And check it out, 3.87. Again, that was done in a matter of not even a second once I pressed compute the standard deviation. Now we have some other measures here. We have the median, the range, the min, the max, etc. But the one we're interested in now is the standard deviation. Super quick. Let's do it for Mom B. Same navigation, Stat, Summary Stats, Columns. In this case, I'm going to choose Mom B. Hit Compute. And here, we'll put it right under Mom A, is Mom B. 5 kids. The average age of those kids, the mean age I should say, is 5 years of age. And as we expected, a smaller standard deviation. You can see here that the standard deviation for the second family that called you is just a little over 1.5 years. And that's because these ages here are much closer together and similar to 5 as they were in the first family, where they were a little more spread out.
All right, so the story's not over yet. It's almost over. Are you ready? You have one more phone call. One more call.
Still on the same paper.
It's Mom C. The Mom C needs you to babysit for 3 hours, etc. You can imagine. She has 5 kids. What's the average age of her kids? 5. Now Now, Mom C had a class in statistics at one point in her education, so she knows that when she starts throwing things out like means and as a way to summarize and not tell you her kids' exact ages, she should probably complement that with a standard deviation. And she does. She goes, hey, the average age of my kids is 5, and the standard deviation is 0. So for some people, this is really easy and fast for them to get. Nobody say the answer out loud just yet. But think about what the ages would have to be such that the mean is 5 and the standard deviation is 0. Then you can decide which babysitting job you'll take. I'll give it to you in a second, but when everybody screams out the answer, some people don't get a chance to process. What are the ages of her kids?
Twins? No, they're
Twins.
kids.
What quintuplets, right? 5-year-olds. That's the only way you can have a standard deviation of 0 is that all of your values are the same. In other words, they're all the same, and thus the same value as the mean. So standard deviation is a measure that will always be positive. It won't be negative. It's engineered to always be a positive number. So the smallest it can be is 0, and you can see the extreme case. And this is a special case. Otherwise, there's really no other way I would know exact ages except for this special case of 0. And it can be clearly as big as, I guess, data that has lots of, spread out big numbers. But it never goes negative, even if your data is negative. Now, if you were collecting temperatures in Celsius in Alaska in the month of January, what are you going to guess? Cold. Cold in Celsius means, below freezing means negative, right? So your whole data set could be full of negative numbers, right? Negative 15 degrees Celsius, negative 10, etc. So the mean's going to be negative, but the standard deviation will be positive. Because all the standard deviation is describing is how different were our temperatures on average from the mean temperature of the month. So that's always even if your data is negative, your standard deviation will always be positive.